Hello and welcome to Chapter 9. Today we're going to look at Lesson 9.2. And specifically in 9.2 we're going to be looking at classifying chemical reactions. So in this section specifically we've talked about balancing chemical equations. Today we're going to look at classifying them so that we can kind of have a better understanding of what's going on, and we should be able to kind of predict our products by the end of this unit. There's going to be 4 different types of reactions that we look at. Okay, we have what we call synthesis, combustion, decomposition, and replacement. So the first type of reaction we're going to look at is what we call a synthesis reaction. This is where you have 2 or more substances that are going to react and produce a single product. So to put it in the simplest form, we have reactant 1 plus reactant 2, or A plus B, is going to yield one product, AB. If you want to look at a visual, we have 2 individuals, and when they become a dancing pair, okay, they're going to make one couple. And just to give you an idea as to what this would look like in a equation setup, notice here we have calcium oxide plus water is going to yield calcium hydroxide. So we start out with 2 individual reactants, and they are going to combine and react to produce one single product. Likewise, for this part here, we have sulfur dioxide plus oxygen gas. These are going to react to produce sulfur trioxide. The next type of reaction we have is what we call a decomposition reaction. And a decomposition reaction is kind of like the name implies, okay? Something is going to be decomposing or breaking down. So the definition of a decomposition reaction says that it's a single compound that will break down into 2 or more elements or new composition. So it's the reverse of a synthesis reaction. And if you look at it in the simplest form here, we have a single reactant, and it's going to break down into 2 or more different components. So if we go back to our example of our people here, you can see that we have this couple, and when they're done dancing, they're going to break up and go off into their own individual little worlds. Okay, so we have a single couple that's going to break down into 2 individuals in this case. When we look at some examples here I have ammonium nitrate. And this is it's a single compound. It's going to decompose, and it's going to make dinitrogen monoxide and water after it's reacted. Likewise, for this second example here, we have sodium nitride. This is going to break down and produce just sodium in the solid state, as well as nitrogen gas in this, or nitrogen. Now this is a special type of reaction that you'll see sometimes, okay? And this is what we call a combustion reaction. Now with a combustion reaction, this is when oxygen combines with a substance and releases energy in the form of heat and or light, okay? So when this occurs, that's just a combustion, and that's usually you'll get your heat, then you can physically feel it warm up. You might see it spark, something might ignite. Okay, that's typically the result of a combustion reaction. Okay, and but on paper, like sometimes you'll see in these examples, it might say plus heat. So if you see that and you have the presence of oxygen, then you'll know that you had a combustion reaction. But sometimes you could also classify this as a synthesis, because if you notice, we have 2 individual substances. They're going to react to produce a single compound. So this could also be classified as a synthesis reaction in this case as well. And the final type of reaction we're going to look at are what we call replacement reactions. And a replacement reaction is just what the name indicates. Okay, a replacement reaction is where something is going to replace an element or elements in a compound. And for our replacement reactions, we're going to look at 2 different types of replacement reactions. The first one we have is what we call a single replacement, and then we also have what we call a double replacement. So for a single replacement reaction, this is where the atom of one element replaces the atom in another compound. So if you notice here, again, we have our simplest form. We have a single element here. We have a compound. Okay, and ultimately what's going to happen when I look from my reactant to my product side is A is going to go in and replace B, and that's essentially going to put B out there on its own. So notice how A goes in and bumps the B value. So over here I have AX now, to where over on the reactant side I had BX. And initially A was by itself, but now at the end B is by itself. So this is what a single replacement reaction looks like. If we come back to the image of our couple, essentially what's going to happen is you have, like, think about it like this. If you have a couple on the dance floor and one person wants to come in and replace one of the dancing partners, okay, now you have a new set of dancing partners, and the kind of like that third person gets the boot, okay, so now he's out on his own. So we have a couple different scenarios that we're going to look at for how a single replacement reaction will occur. So for this first one, notice we have a metal that's going to replace a hydrogen. So here I have a single metal and I have water, H2O, and what's going to happen is a lithium then is going to literally go in and replace one of the hydrogens. When that happens, we're left with lithium hydroxide and just hydrogen gas on its own. So again, lithium replaced a single hydrogen to form lithium hydroxide, and it kind of booted one of those hydrogens by kind of out on its own. Now in this case, hydrogen, remember, is a diatomic molecule, so it will not appear by itself, and that's why I have an H2. And then we would go ahead and balance the equation like normal. We also have the case where a metal will replace another metal. So in this example, I have copper and I have silver nitrate. So copper is literally going to go in and replace silver. So that's going to boot silver out to be on its own. So I have silver by itself over here, and then I have my copper nitrate. Now for our final point of discussion here, we have a nonmetal replacing a nonmetal. And we actually have two different scenarios that we're going to look at. Okay, so if we look at this top equation here I have fluorine, okay, all by itself, is going to replace another nonmetal, which in that case would be bromine. So fluorine's going to come in here and replace bromine. So I end up with bromine off by itself over here, and I have sodium fluoride. Okay, pretty straightforward. Now another thing that you're going to see sometimes is if I go and I try to reverse this reaction, here I have bromine by itself, and theoretically we would think that bromine would go in and try to replace fluorine. However, if this occurs, we get this little notation here that says NR. So NR really means no reaction. Okay, so if you look at this here, in the first equation, fluorine could go in and replace bromine. However, if I were to try to reverse that, bromine cannot replace fluorine. Now, one thing I want you to know is not every nonmetal will replace another nonmetal, and not every metal will replace another metal, okay? There is what we call an activity series, and this activity series will help us determine what's going to react and what will not, okay? And this is a sheet that I will give you when we are in class. You can use it on a test and a quiz. And probably the hardest part is just remembering to reference it to see if something's going to react or not. So, as we just mentioned, a metal will not always replace another metal, okay? And this is due in part because of the difference in reactivity, okay? And reactivity is what we call the ability to react with another substance. So if you look at these two charts right here, these are our activity series of metals. And again, this is something that I will give you on a test or quiz. I will also give this to you when you guys are back in the classroom. But essentially how this works is, notice if I look at this big one over here, okay, we have a list of metals here on the left side, and then we have kind of some descriptions over here on the right side. So our most active metals are going to be at the top, and our least active metals are going to be at the bottom. So how this is going to work is a metal above can replace any metal below it, okay? But a metal like sodium could not replace a lithium, but lithium can replace a sodium. Okay, and notice in this category here, again, I will give you this exact table so you have to know how to use it. It says that all of these elements here will replace the hydrogen and water and acids, and each replaces metals listed below it. So lithium can replace a rubidium, a potassium, a calcium, or a sodium. Potassium can replace either a hydrogen and water and acid or calcium and sodium. Okay, and again, anything down below too. So notice when I get to this group of metals here, it says that these metals will replace the hydrogen in acids. Okay, doesn't say anything about water, but it just says in acids, and each one will replace the metals listed below it. Now when we get down to this group here, it says all are mostly unreactive as far as replacing other metals in a compound. So pretty much copper can replace a gold, but when you get down here to gold, gold is not going to replace anything else. Okay, and that's similar to our halogen activity series. Okay, fluorine can replace anything below it, but iodine is not going to be able to replace anything above it. Okay, so, and it tells you again right here, it says each replaces halogens listed below it. So again, you just have to understand how to use a chart, and then you guys should be all set going forward. So for example 1, it says predict whether the following single replacement reactions will occur. If it occurs, we're going to write a balanced equation for the reaction. So in this case, I have potassium plus zinc chloride. So here I have a metal, and that means that we got to look and see if it will replace this other metal. So if I come over here and I find potassium on my list, so I have potassium is right here, and it's going to try to replace zinc, which is down here. So potassium can go ahead and replace zinc, okay, because zinc falls below potassium. So what that tells me then is potassium is going to become KCl, and remember, potassium has a +1 charge, chlorine has a minus. I still have to do the crisscross, so I end up with KCl plus, and then it's going to boot the zinc out on its own. So now that I have my equation written, all I have to do is go in and balance it. And when we balance it, you're going to end up with 2 potassiums plus zinc chloride yields 1 zinc plus 2 potassium chlorides. For part B, we have chlorine is going to react with hydrofluoric acid, and we have to see if this is something that's going to react. So I have chlorine, and this is a halogen, and so is fluorine. So I have to look and see, will chlorine indeed replace fluorine? Well, chlorine is right here, and fluorine is right here. Chlorine would be going up to fluorine, and so because chlorine is below fluorine, this tells me that I'm going to get no reaction. And you can either write out no reaction, or you can just write NR. For part C, I have aluminum and lead nitrate. And so that means I have 2 metals. So I have aluminum and lead. And I'm going to come over here, and I've got aluminum here and lead down here. So because aluminum is above lead, that tells me that that's a possibility. So I'm going to end up with aluminum replacing the lead. So I have Al, which has a +3, and I have NO3, which is a -1. So I have AlNO3 plus lead, which will be on its own. And now we can go ahead and balance this. And when we balance it, we end up with this equation right here. So here are the 3 equations that we just balanced, all on one sheet. Please let me know if you have any questions on example 1. The last thing we're going to look at today are what we call double replacement reactions. And these are very similar to single replacement reactions, except we have 2 elements that are going to be exchanged. So if we take a look at our simplistic form here, we have AX plus BY. And ultimately what's going to happen is the A and the B are going to be switching spots to produce AY and BX. So from a picture standpoint, this would be like if you had 2 groups or 2 couples that were dancing, and they just ended up going in and switching partners then. So in the case of this picture, the guy in the green shirt then is going to come in and replace the girl in the blue shirt, and they would now have 2 new sets of partners. So if we look at the scenario where we have a metal that replaces a hydrogen, we have this metal of calcium is going to go in and it's going to replace a hydrogen, and essentially that hydrogen then is going to replace that calcium. This is the double replacement. So we end up with calcium chloride because the calcium is going to replace the hydrogen, and then our hydrogen is going to replace calcium, which is going to leave me with HOH, which is really H2O or water, and that's what we end up with right here. Now, when we look at equations with double replacement reactions, again, here notice I have sodium and copper. Sodium and copper are actually going to switch spots here. Okay, so when this happens, I end up with sodium chloride and copper hydroxide. Okay, and the one thing I would like for you to kind of take a quick note of is notice I have an aqueous solution of sodium hydroxide. I have an aqueous solution of copper chloride. This produces an aqueous solution of sodium chloride and a solid solution of copper hydroxide. Okay, so we started out with two liquids, but we ended up with a solid and a liquid on the product side. So we ultimately ended up with a solid that was formed as a result of these two compounds being mixed together. When that occurs, that solid is what we call a precipitate. And I want you to note that all double replacement reactions are going to form either water, a precipitate, or a gas. So we have a series of steps when writing double replacement reactions. The first step is going to be to write the components of a reaction in a skeleton equation. So here you can see that we have aluminum nitrate plus sulfuric acid. The second step then is going to be to identify the cations and anions in each compound. Because remember, in order for an ionic compound to become neutral or balanced, we have to have a positive and a negative together. So if I look at my ions, I know that aluminum and nitrate have to either form a group, or aluminum and sulfate, because I have to have that positive negative. I can't have aluminum and hydrogen coming together because that gives me two positives. Okay, so I break down my ions into individual ions. Then we're going to pair up each cation and anion from the other compound. Then we're going to write the formulas for the products using the pairs from step 3. So here we've got aluminum sulfate, and remember you have to crisscross, and I have nitric acid. Then we're going to rewrite the complete equation for the double replacement reaction. And then our final step is going to be to balance that equation. So once you've done this, you are able to do a double replacement reaction, and everything was balanced, which is exactly how we need to end our problem. So just as a quick review, we have 4 different types of replacement reactions. Of reactions. We have the synthesis, where we start out with 2 individual pieces, and they're going to react and form one piece. We have the opposite of that, which is a decomposition reaction, or we have one individual piece and it's going to break apart into 2 or more. Then we have our replacement reactions, where we have the single replacement. So one part is going to go in and replace the other part, and then that other part is just going to be left out on its own. Or we have a double replacement, where 2 parts are going to be switching to create 2 new things over on the product side. And just one more visual to kind of help you see what's going on. Here's another table. It gives you the different reaction types. Okay, it gives you the technical definition, and then it shows you another visual. Please let me know if you have any questions. Otherwise, I hope you guys have a great day, and we will see you guys in class.